Okay, so this is chapter 31, interactions between a binary and a quantitative variable. Remember that multiple regression forces the same slope for all levels of each variable. They have parallel slopes, and in the last example, in chapter 30, that was appropriate. We were looking at a similar survey from a different semester that had this negative correlation between the size of people's feet and how many shoes they buy. And we realized the gender was the confounder. And when we stratified on gender, that relation went away for both males and females. But now we have a slightly different situation here where it didn't quite altogether go away for females. The slopes aren't the same. You can see that for females, they're slightly different. It appears that foot size has no effect on the number of shoes males have, but it has a slight negative effect. Maybe, as I say here, maybe it's the Cinderella effect. So what do we do? Well, what we have to do when the effect of one variable, shoe size, on one differs, when the effect of one variable on y differs depending on the value of the x variable, in this case between males and females, we say there's an interaction effect. Okay? So we're going to have to add an interaction term to allow for different slopes. So you can see here, you can see that these are the stratified regression equations. And you can see that they have different slopes. The male slope's almost non-existent, whereas the female's has a slight negative slope. So the picture, an exaggerated picture, would look something like this. Okay, so there's shoe number and shoe size. And shoe number and shoe size. And we have this is shoe size, and this is shoe number. And we have the females up here, and they have a slight, with small feet and more shoes, this is exaggerated, and they have a slight negative correlation. And then the males down here with bigger feet and not as many shoes have a pretty flat slope. It's a tiny bit positive. So these different slopes, to allow for these, we're going to have to add an interaction term. But you can see, so there's confounding as well, though, because gender is still a confounder, because the overall slope is much more negative than the slight slope here. It's certainly not the average of the two slopes. So there's interaction and confounding here. So there's an interaction, non-parallel slopes, and confounding. All right, so what are we going to do? Okay, so what we'll do here is we are going to add this interaction term. So here, let's see, so we have here's the slope for gender, x1 is gender, and we'll color this. This is shoe size, make that orange, and then we're going to add this interaction term that's x1 multiplied by x2. It's a multiplicative term here, and that will have a slope too. So here's the shoe size, okay? So we can find this multiple regression equation by combining these two simple stratified regression equations. So here's the two simple stratified regression equations right here. Now notice these don't confuse these stratified regression equations with, they both have shoe size. They both have shoe size, the same x variable, predicting y, shoe number. Don't confuse those with the two simple regression equations we saw at the end of not chapter 12, no, at the end of chapter 30. Each making predictions from a different x variable, gender or shoe size, okay? So in this case, we're combining these two stratified simple regression equations into a multiple regression that will give us exactly the same information. In the previous case, when we combined two simple regression equations, one predicting shoes, one was shoe size predicting the number of shoes, and the other one was gender predicting the number of shoes. And that gave us more information because it gave the effect of each variable after controlling for the other variable. So here we can get this. We can get a multiple regression equation that will give us exactly the same information. All right. So how are we going to do this? Since x1 right here, this x1 is 0 for males. This one right here, x1 comes up here and there. And it's 0 for males, so males equals 0 here. Males equals 0, and female equals 1. And this is our x2 variable. That's there and there. All right. So how should we fill this in? Since males is 0, let's fill them in first. Those two will disappear. And so we'll take this male equation and just match it up here. So it's 5.849. Okay, so when males are, when males are 0, these males will disappear, and we'll just have 5.849 plus this slope, 0.06555. So that fits the male equation. Now for females, what do we want? Well, for the intercept, we'll want this together to be 29.24. So when females, you put a 1 in there, 5.849 plus what equals 29.24. So that's 23.39. Those two add up to 29.24. So now we also want a slope, these two together, we want to be negative 1.117. So we want it to be negative 1.117, so we're going to have to subtract that off, right? So that plus negative 1.18255 equals that. All right, so that works because when x1 is 1, these two together give the intercept, and these two together give the slope. So let's see if that agrees with what the data program gives us. So the data program, let's look down here. It gave us an equation. It has 4 parameters here. These are 4 parameters. There's a beta naught, a beta 1, a beta b2, and a b1, b2. Slope, you can call it b3. So there's 4 parameters here. And here's the shoe size. And here's the gender. And here's the multiplicative effect of both. All right, and it turns out when we look at this, this was not significant. This is very significant, gender. And this is significant, the interaction term, but the shoe size drops out. So only gender and the interaction terms are significant. Shoe size is no longer significant. Shoe size hardly matters once gender and the interaction term are in the model. All right. So just to make it clear, what we should say that we want, okay, so here, we want negative 1.117 when x1 is equal to 1. That's what I was doing here. And we want, here we wanted 29.24 when x1 is equal to 1. All right, so that's how we got this. And you'll have homework similar to this. So let's turn the page. And so sometimes people get interactions and confounders mixed up, but they're not the same. As you can, and here's a nice visual explanation of that. So, so let's say we're trying to figure out if x causes y, and the data consists of these two prior groups, okay, A and B. Now, combining the two groups can give you an overall regression effect that's misleading when there's an interaction and when there's a confounder here. So, so how are we going to look at this? Interaction is when x has a different effect on y for group A than it does on group B. And it's illustrated by non-parallel within-group slopes. And confounders is a difference between A and B that's influencing both x and y. So for each of these, indicate whether they have only confounding, only interaction, both, or neither. All right, so here's a y and here's the x-axis. And we can see, so there's two groups. Say there's group A and group B. All right, and you can see that both of these have about the same slope. So that means there's no interaction because they have parallel slopes. But now, how do we figure out whether there's confounding? Let's look down here. Okay, can you see that? Yeah. So interactions is different slopes within the groups. Confounding, both these conditions have to be met. Different x-averages for the two groups, and the overall slope is not equal to the weighted average of the two group slopes. So the overall slope, I'll mark that with yellow, and the weighted average of the two groups I'll mark with orange. So this is the overall slope, and this, the orange, will equal the weighted average of the two group slopes. All right, so let's do this. So here, what is the overall slope? Can you see the overall slope looks like that, right? Because this is basically one clump of points and that's another. So it looks like a positive overall slope. That's confounding. And there's different x-averages right here. So the two conditions are met. So they're certainly confounding. Now, what is the average? This overall slope is not equal to the average of the two group slopes. Well, both the average of the two group slopes is just a flat line because both group slopes are flat. Okay? So this is only confounding. I mean, yeah, only confounding. There's no interaction. You can think of this as one clump and that's as another clump. All right, how about this one? Well, this one, there's no interaction. They have the same, A and B have the same, here's these two groups, have the same slope. And there's no, they have different x-averages. But the second condition is not met because look, the overall slope is like that, and it's the same as the average of the two group slopes. It's the same. So there's no neither. interaction or confounding. Okay, let's look at this one. This one has different slopes, right? So there's certainly an interaction, right? Now, is there confounding too? Let's see, they have different x averages. And the other condition is that the overall slope, and the overall slope looks like that. That's the overall slope, is certainly different than the weighted average. Here's a flat slope and a negative. It's going to be, this will be the weighted average, will be sort of in between those. So it's certainly different. So this has both an interaction and confounding. How about this one? This one certainly has an interaction. Look at that. Certainly has an interaction. They have different effects, right? Different group slopes. And but they have the same x average. So there's not going to be confounding. They have the same x average. And also the overall slope is the same as the weighted average of the two slopes. There's the overall, and there's the weighted average. So basically, what this says is that as there's two different groups. There's a group A and there's a group B. And here's A and here's B. And as x increases, for group A, y decreases, but for group B, it increases. So overall, it has no effect for everybody, but for the individual groups inside there, it has an effect. I mean, it's analogous to polling. Like you could have a pre-election poll, you could have the Democrat and the Republican be tied, but that doesn't mean that within the subgroups it's going to be tied. For Republicans, they're going to favor the Republican candidate, and Democrats are going to favor the Democrat candidate. So you can think of them as having, subgroups can have very different effects, but overall, they're tied. And it's sort of a similar situation here. This confounding really messes things up and makes and gives you is not only misleading, it's wrong. I mean, it's saying, for example, here it's saying that there's a positive relationship when it's not positive for anybody. It's just nothing. And here it's saying overall there's a positive when it's either flat or negative. So it's bogus. Whereas interactions, like here, there's no confounding. This basically says overall, if you average the A and B together, groups together, this X has no effect on Y. That doesn't mean it has no effect, but within each subgroup, it has an effect. All right, so that's chapter 31. Now here's the summary for 31. And let's see. So a linear model with just the main effects, has none of this multiplicative term, okay? And these x's can be either categorical or quantitative. But a linear model with main effects and an interaction term has this multiplicative term here, all right? And you add that interaction term if you think the effect of x1 on y changes depending on the value of x2. So let's see. So we looked at this number of shoes with just an additive model with no interaction effect, and we saw that it's best fit simply adding the two main effects. And the slope this is the same slope. We had the same slope for both males and females. And this right here is the intercept, the change in intercept, the difference in intercepts between males and females. But when we have an interaction term here, we have both a change in intercept, like here would be the change in intercept right here, and we also have this effect, which is the change in slope. This slope, change in slope, that allows for the difference in slopes between males and females. Okay, the difference in slopes. Okay, let's move on. Now we're going to do chapter 32, which is regression with two binary predictors and a quantitative response. So here's an example. Suppose subjects were divided randomly into 4 groups. They were given drug A only, drug B only, both drugs, and neither. And the duration of some disease was recorded. The tables below give the mean response for the three types of models. All right, so the first model is just an additive model with no interaction term, okay? So, so here is the model here, and it says, okay, the drug, your disease lasts, let's say it was a cold, lasts 10 days without the drug, and with drug A, it gets reduced by 4, and with drug B, it gets reduced by 2. So if you took them both together, you'd go down by 6 to 4. All right? So it's a very simple model here. It says, you know, when you plug in 0 right here for A and B, you get 10. If you just plug in, if you have B be 0, 10 minus 4 is 6. If you have A be 0, 10 minus 2, 10 minus 4. And here is if you have 1 for everything. So you put a 1 in here, and you have 10 minus 4 minus 2. And you get that. So it would look like parallel slopes. If I wanted to graph it, I could graph, let's just graph A with no B first. So you have here A is either 0 or 1. And the duration of the disease goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it starts off with no drugs at all, no A and no B at 10, and then if you administer A, it goes down to 6. So 1, 2, 3, 4, 5, 6, or 6. So we go here. So it looks like that, 10 to 6. That's when B equals 0. All right, how about when B equals 1? So when B equals 1, right here, and no A, and B is 1, it goes down by 2. It's 8. It starts at 8. And then if you add A, it goes down to 4. So it's the same slope. It goes down to 4. Eight minus 4 is 4. So it's the same slope here. See? Parallel slopes. Okay, so that's parallel slopes. Now let's add an interaction term here. Okay, so what would we put in here? So here it's the same. 10 minus 4 equals 6, and 8 minus 2 equals 8. But now it's not going to be 8 minus 4. We're not going to have, we're going to subtract off more. The effect of the 2 drugs is better. It lowers the number of days you have the cold. So it's, it has, you know how this happens all the time with drugs. You take 2 drugs together, sometimes they have a synergistic effect. They have a better, more than the sum of their parts. Or more often they say, you know, you're taking one drug, don't take another drug because they'll have a bad effect. So it's worse than the sum of their parts. Okay, so now let's look at this one. And what are we doing here? So right here is when A and B are both 1. So if you put in a 1 for both of them, what do you get? You get 10 minus 4 times 1. minus 2 times 1 minus 3 times 1 times 1. And so that is 1. So you go down by 7 here, not 4. So this is what it would look like. The same thing, but there's going to be, so this is A, 0, and 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's where you start off at 10. And you go down to 1, 2, 3, 4, 5, here's 6. So you go down here. So this is when B equals 0. Whoops, this was B equals 1 here. And now when B equals 1, what happens? We start off at 8 here with no A. But now you go all the way down to 1, and that's minus 7. Down to 1 down here. So these are non-parallel slopes. So these are not parallel. All right, and you can do the same with this last one. This one says that the effect of the two drugs is worse than their individual effects. So let's look at this. So now we'll do the same thing. We'll put in a 1 for both of them. We get 10 minus 4 minus 2 plus 7. So that is 11. So it's worse than if you took nothing. Your cold lasts 1 day longer. So let's graph it, and you'll see they're non-parallel slopes. So 0 and 1. There's A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we'll start off at 10. And we go down to 6. Now we start off at 8. And we go up to 11. So it's worse. So that's when B is equal to 0, and that's when B equals 1. And again, these are non-parallel slopes. So this is a very simple case of something called two-way ANOVA, because we have two binary predictors here with a so the two categorical variables predicting a quantitative. Okay, let's see what else there is here. Okay, so let's do some. This is going to be very similar to your homework. So all right, so A and B are two treatments designed to boost scores on some exam. Coded 1 if given, 0 if not. The numbers in the table indicate the average boost for each treatment by itself, from both together, and from neither. All right, so fill in the blanks to make so the model and the data match. Well, this is pretty easy to do. All we have to do is fill in this blank, and that's when A and B are both 1. So you put in a 1 and 1, and you get 50. And you can see there's no interaction here, no interaction term. Parallel slopes, 0 plus 20 equals 20, 30 plus 20 equals 50. All right, how about here? Well, it filled everything in for you. We just have to fill in the number here. So let's see. Well, this is when everything, a 1 here, a 1 here, and a 1 times 1 here. So we get 50 plus what's going to give us 60. So that must be 10. So that's our interaction term. So now, how about this one? Well, when A and B are both 0, get rid of those, we have 2 here. When B is 0, but A is 1, we get 8, so it goes up by 6, 2 plus 6. There. And when this says A is 0, a is 0. So when a is 0, 2 plus what here? Has to be 8. Gives us 10. And there's no interaction term. So 2 plus 6 plus 8, and then we should fill this in as 16. And there's parallel slopes, both directions, see? Okay. I mean, if you coded B, you could have done a graph with B instead of A, and then you would have gotten slopes of 2 here. Okay. And let's see, how about this one? Well, this one is pretty easy. Again, what do we have? We just have to put a 1 in here and a 1 in here, and we get 55. All right, how about this one? All right, so for here, you have B equals 1, but no A. So B equals 1, so here's your 30 minus, so, but A is 0, so that goes out. So, see, it's a 0 times 1, and that's a 0, and that's a 1 for here. So you get 30. And here you put 1s in for everything. And you get 50 minus 10. And so that's 40. And finally this one. All right, when everything's 0, you get 10 here when it's all 0. When you get rid of the b's, put zeros in for the b's. You just get a total of 12, so that has to be a 2. And 10 plus, you can just see 10 plus 5, so that has to be a 5. And this has to be what? You have 10 plus 2 plus 5 plus what equals 9. So that's 17 minus 8 equals 9. All right, and the last one is right down here. And it's the same thing, 10 plus 2 here, and plus 5 there. So when b is equal to 0, this is the same thing, it's 2 and 5. But now we have 10 plus 2 plus 5 plus what equals 20. So this has to be 17 plus 3. All right, so that's the idea. It's kind of fun. And you have homework like that I'll post. All right, let's turn the page. And let's just do one more chapter and then stop. And this is going to be a short lecture. So, in simple regression, we drew. So what are we doing here? Now we're going to have we're going to have quantitative x's. So far, we've had multiple regression with binary and a quantitative, or 2 binaries. But now let's just do it with 2 quantitative x's, okay? So before we drew a scatter plot to show the relationship between 2 variables. Okay, if it was roughly linear, we estimated by this regression equation. All right, so this is just a line like this. That's what we're doing here, just a scatter plot in 2D. But now we're going to be in 3D because we're going to add another x variable, 2 explanatory variables. So now our equation is of this form. So for example, let's say we go back to, we've looked at homework predicting finals. That's the last thing we did last time. And exams we've looked at a bunch of times predicting finals. So here's the same data set. Now we're going to look at 2 variables predicting one. Whoops. We're not going to predict homework. Here's our 2 variables, x1 and x2, predicting y. Okay, And now we've got a stronger correlation than we did with just either one of them. Okay, and we're going to have, these are slightly different data sets, unrounded numbers. I think we got 0.6 when we just did exams, so slightly more when we added in homework. So now for simple regression, the correlation coefficient is, remember, it's the product of the z-scores, and then you take the average of that. And so it's really only defined between two variables, x and y. That's correlation is just defined between two variables. So what do we do when we add a third variable? For multiple regression, the capital R is the correlation between two sets of numbers, but it's between the actual y's and our predicted y's, because we can't have correlation between three sets of numbers, between x1, x2, and y. You can only do it between two sets of numbers. Okay, so y hat is the predicted y's from our regression equation. So it looks like this. It's the average of, once you change to z-scores, the y's, our actual y's, and our predicted y's. Okay? And it's only, for simple regression, this is actually the same thing as just the positive R. R can be negative or positive. It ranges between -1 little r and +1, but big capital R, when it's the correlation between what we're predicting and what our actual values are and what we're predicting them, it's always positive because we want our predictions to be close to the actuals. I mean, they're going to be close to each other. If it was, I mean, we can have a negative slope, a negative correlation between the two variables, but we want our predicted y's to be close to the actual y's. So that will always be positive. Okay, so what would it look like? Suppose we wanted to predict the final scores from homework and exam averages using an equation of this form. So let's look at the 3D scatter plot and see what it looks like on the next page. So here's what it looks like. Okay. So here you can see that given people's exams, that in this case range right here from 50 to 100, and their homework, which range from 30 to 100, we're estimating we're going to estimate their final scores. And here's their actual final scores. Here's the actual points. So the scatter plot shows their final exam scores as the vertical distance from their point in the homework exam plane, in this plane. So like this person right here got like, what, a 65 on the homework? Like it's 72 on the exams and did terrible. Probably about a 40. It starts at 40. Really flat. 40 on the final. Whereas this person, what did they do? That person has a terrible homework score, but got a really high final and a high exam score. Okay, so well, no, not so high, but let's see. You can see it much better here when you draw the vertical. Look at that person. So much easier to see here. So here you can see. So he had a 80 on the exams, about a 45 on the homework, and then he aced the final. Okay, so can you see this? Let's see. So the multiple regression equation right here is the best fitting what? Do you know what that would be? What if we wanted to fit the best? It's not going to be a line. Do you see how it would be the best fitting plane through all these y's so as to minimize the squared errors in the y's? That's what we want. So this is like this is homework. This would be x1. And this is x2 is the exams. And we're predicting finals, which are y's. All right, so let's look at that plane. And here, can you see it? Let me see if I can focus in on it. Yeah. So can you see that plane in your, let's see. Here's a picture of the plane that minimizes the sum of the squared errors in y in the finals. See how the slope of the homework is the tilt of the plane as you go from 30 to 100. So the tilt of the plane, so it's this. Right there. That's the homework. And you see it has a pretty small tilt. And here, the exams are better predictors of the final. These are the exams. So it has a stronger slope. We can compare the tilts because all the variables are expressed in the same units. Okay, so that's pretty much it. And then we're going to look at how we get those slopes and something called the correlation matrix between all three variables. But I think we'll do that after break. So this is where we'll start after break. And have a great break. See you.